So here's assignment 2. We're going to start with a container that's 0.1 uh, millimeters cubed in volume, and you have water and air in here. The water weighs 1 kilogram. Here's our water, and here's our air. Water weighs 1 kilogram, and then we're given an initial temperature and an initial pressure of initial temperature 298 Kelvin, and an initial pressure of 101.325 kilopascals. And then we're also given in the start of it, we are given another pressure. So our pressure final is going to be equal to 200 kilopascals, but we don't have a final temperature. This is what we're going to be finding right here. Right here, we want to find our final temperature, considering this volume, this weight of the water, and our initial values, our initial temperature and pressure values, and then our final pressure value as well. So what we're going to be looking at here is how to find this final temperature. And the first thing we're going to want to do is add our water and our air pressures together. So the pressure final is going to be equal to the pressure of our water, pressure of H2O, plus the pressure of our air. And this is mainly what we're going to use to help us find that final temperature. And we're also going to use the equation PV equals nRT. This is to do with pressure, volume, temperature, and everything in between. So these two equations are going to help us immensely in the future. So we're also going to be using with our PV equals nRT, we're also going to be using the constant 8.314 joules per mole Kelvin. This constant is going to help us figure out what our ultimate equation is going to help us give. We're going to state this right at the beginning, and we're also going to find out with cancellation that Newton meters equals joules. This is also going to help us find our pressures and volumes. Now what we need to do to find the number of moles of air is take PV and PV equals nRT and switch it up a little bit. So we're going to say the pressure initial is going to be equal to the pressure of the water, H2O, plus the number of moles of air times RT divided by the volume of the vapor phase. So this is going to help us get our moles of air, and this equation is going to be beneficial because we have the initial pressure and we have the pressure of the water, and we can find our moles of air for this. So yeah, that's going to help us. So what we're going to do to start is we are going to get our data. We're going to start to get our data from the GitHub site. So we're going to come up here and we're going to say, we're going to find our GitHub site right here, Control-C, Control-V in here. But we just want it to be, we just want the tools and the data. So we're going to say .git, and that's going to help us. But we need to grab it. So we need to say git clone depth step one, to get our, so we're going to say run, to get our data. Now, to continue to obtain our data, we are going to import our SYS. So we're going to say import SYS, and then we can say sys.path insert, and this is going to be our one value, and then we're going to grab it from content, and then our CHE tools. And after that, we also need to import our tools, so what we're going to be using. So import tools.che has our CHE. CHE. Okay. We add more code, and we're going to put in our equation. So P equals CHE of our props, but that's going to be our water. So I'm going to say, okay, water. We need to add our these. Okay, and that should just, yes, okay. Good. Okay. So what we want to do here is we want to optimize our equation. So we're going to say from our SciPy optimize, we import our roots that we're going to find. And we are also going to state our R value, which is the 8.314 from earlier. 8.314, and it's going to be in joules over moles Kelvin. Now we're going to add some code, and this is going to be all of our values that we've been given. So it's going to be our V, the total volume, which is 0.1, and then the weight of the water, which is 1 kilogram, and the initial pressure, PI, is 101.13, but that's kilopascals, so we're just going to use pascals, 325 pascals, and we're also going to use our pressure final, which is going to be 2e to the 5, which is 205 kilopascals, and then our TI, our temperature initial, these are all been given to us, 298 Kelvin, which is our initial temperature. Now we are going to input our density. So this is going to be P dot RHOL of our initial temperature. Got to make sure it's case sensitive. And we also want to use our NAIR code and to input our equation. So it's going to be our initial pressure minus the vapor, the pressure at the vapor rate at our initial temperature, and then that is going to be multiplied by the volume, the total volume. Sorry. Minus the initial weight divided by our P RHOL, which we just defined up at the top, times the initial temperature divided by our R times TI for our equation. Yes, so that should be working, and then we're going to go to our code and we're going to input NAIR and see what we get. So we're going to go up here, say run off. And we have some errors here. So after we have this our equation in here,
for PV equals PV times nRT, we're going to go into our def PEQ of X. And this is going to give us a chance to import our values once again into a graphical sense. So we're going to say our temperature final is going to be equal to our X, but we need to say of 0. And then our volume of our vapor phase is going to equal the vapor total, or the volume total, which we know is 0.1 minus the weight of I, or the weight initial, I mean, and then times our P, R, O, H, or HOL value of our temperature final. So after we have this, we have our pressure of the water. This is going to give us our pressure at the vapor phase at our temperature final. And we're going to have our pair equal to our Nair, I think temperature final. This is going to get us our the partial pressure of water, or the partial pressure of air. And we're going to return pressure of the water plus pressure of the air minus the pressure final, because the pressure final is equal to the water pressure plus the air pressure. Next, we need to say that our root, because that's what we're looking for originally, our root of the PEQ that we just defined is going to be our X, and then our Y is going to be our TI. So here we go. Yeah.